you need to have so many wires, and let's say for example you have one wire disconnected, right? One wire from the data bus disconnected, alright, and then your system will not function at all, alright. So to minimize that, so they have already embedded everything inside, and they already done the wiring inside in a single chip, right? So this is the microprocessor, the SRAM, right, the flash, okay, and you can also see some other features. The main features that we have understood is, of course, the RAM, the RAM and the ROM. The flash is the ROM, right? Flash is the ROM. RAM is random access memory, temporary, and the flash is the read-only memory. Right? And you can see over here the data bus between the exchange between the of data between the SRAM and the microprocessor, and also in the flash over here. Then you can see some other peripherals, right, such as the A to D converter, analog to digital converter, right? So in many applications today, um, uh, it is almost impossible for us to avoid analog signals, because analog signals are the real world signals that exist in our real world. So you use sensors that you learn in electronics and instrumentation, and you convert, you capture those signals from those sensors, you amplify, you do filtering, you do subtraction, things like that, and many other processes in the circuit, and then you get your final signal, right? For example, your ECG signal, and then your ECG signal will be for you to actually to do processing of your ECG signal, right, which you will take during the subject of biomedical processing, right? You need to convert the signal into digital, the analog signal of the ECG into digital. Can I draw this? Right, let's say you have an ECG, right? So you're going to convert all this analog value of voltages into the microprocessor, right? And for microprocessor, usually if you use normally it is powered by 5 volt, 5 volt, right? 5 volt. Right, so what you want to do during your circuits in instrumentation is you will need to amplify as much as possible, so that your signal, your ECG signal, your EMG signal, your EEG signals, so that it is within the range of or in between 0 to 5 volt, right? You want to do that, you want to do that, and then from here, then only then you can capture your signal into the microprocessor, and you will get the digital representation of values of this signal. So these signals, if you are familiar with MATLAB, because these digital values they are numbers lah kan, they are numbers 0, 1, 2, 3. For if it is an 8-bit, it will be 255. The number will be 255. If you have taken MATLAB before during the lab, MATLAB. So in your ECG file, you have a series of numbers. So it's just numbers. You cannot see anything. But when you take those numbers, those digital numbers, you plot them using the MATLAB plot instruction, and then you see from these numbers comes out a signal, an ECG signal. Right, but at that point in MATLAB, it is no longer an analog signal. It is a digital signal. It's a plotting of digital signals of the ECG, but it's no longer an analog signal. Analog means it is the signal, the actual signal outside the digital world, which is in our, right? And Okay, can I remove this pointer? Okay, so other than that, you can also see the other peripherals, like here you can see an EEPROM, right? EEPROM over here. You can see uh, USAT, USAT or OWAT. This one, if you have done your Arduino previously, when you connect your Arduino board using the USB cable, you connect it to the PC. Alright, so it's actually your Arduino board is actually consists of two, what you call it, two elements. Actually, your the UART and the converter of from UART to USB. Alright, so because most of our PCs now and your laptops too, you no longer have the UART port. You no longer have the COM port. You no longer have the physical COM port. Alright, but most of our laptops now have the USB. But for microprocessors and microcontrollers, right, they have the USAT or UART module. This is in the format of COM port, we call it serial COM port, and therefore in on your Arduino board, if you look carefully, there's a UART to USB converter, right? You can also look for modules. Modules, a very small one now costs around 10 to 20 ringgit. During my time in 2004, UART modules cost like 200 up to 400 ringgit, very expensive. Now it's very much cheaper, right? Because everything is made in China, right? So China have all those designs, very good, right? So they have the UART converter, which converts to your USB lah. So uh, so actually it's not a USB. So basically it is a UART. So this UART is where you send your data from the RAM, alright, or from the flash. You send to the UART, and the UART will send your data out into the physical wiring, right, into the we call it the UART to USB converter, and then through the cable of the USB connect to your PC. Alright, and your PC will then detect as a what you call it, they don't usually for UART to USB converter, they on the PC side, we will not detect as a USB device, but it will detect as a USB to serial interface, USB to serial or serial to USB connection, right? Whereby the driver for the laptop emulate the function of a serial COM port, which is matching to the UART, but it is a USB, but it acts as a UART receiver, and then therefore if you do some programming like MATLAB, you can use your serial COM port library to read data from the virtual UART uh, of the USB to serial connection lah. Right, so UART is used for you to send data, right, from your board, send to and from, send and receive, to and from data from the internet, so not the internet, your PC, or it could be also you want to connect one microprocessor board to another microprocessor board, right, using UART without actually uh, needing for you to have USB. So UART, you can connect this processor UART to another processor with a UART also. So no need for USB, right? So usually UART is to connect between microprocessor boards or microcontroller boards. All right. And then here we have another interface, which is the SPI. All right, SPI means serial peripheral interface. Serial peripheral interface. It is also in the form of serial communication, but usually they use SPI for you to communicate between ICs, between ICs on board. Let's say you were to have let's say you were to have some um, let's say you were to have some IC, IC. All right, some of you for your CDIO, right, you might use accelerometer, for example. So that would be usually the most popular one would be the MPU, right? MPU 6050, 6050, right? So it is an IC, right, which actually it has analog circuits inside. Right? This is IMU, the IC lah. So this IC measure motions. What happened here, I'm not sure. So this IC will measure motions. It has very tiny micro micro electromechanical sensors inside the chip. So small changes of the mechanism inside the chip will be detected lah, in the form of XYZ motions. And then inside the IMU, they also have all the analog circuits, and they also have the built-in analog to digital converter. So this IC the MPU 6050 will output digital data. All right. So you need therefore for you to get the data from the IMU to get into your microcontroller or microprocessor. All right. You will need to connect through this digital interface lah, which is one of it would be the SPI, the SPI connection. So you have around 4 pins, 4 pins. This one you will look specific in detail later. You have MOSI, MISO, S clock, and SS. Right. So you connect all these digital lines into the MPU 6050, and it will be you will be communicating using the serial protocol. But the serial protocol of SPI is different from serial protocol of UART. It is different. The protocol we'll discuss that later, but it is different. And the speed is also different. The SPI, the speed is in megahertz. In megahertz, that means the speed of transfer data is in megahertz, very very fast. Whereas for UART or USAT, the communication, the fastest would be in hundreds of kilobits per second, right? Hundreds of kilobits per second. So compared to megahertz, or megabits per second. So SPI is faster lah. The only difference is that SPI, because it is very very fast, you cannot transfer those serial data through any cables, through any long cables. You will not be able to do that. So along the way, if you have high speed data, electrical data along your cable, that your data will be interfered by noises or interferences outside uh, uh, in the environment lah. Right. So megahertz electrical signals in wires are usually not suitable. So if you want to connect between two microprocessor boards, let's say in the range of 50 to 100 meters, you can use UART. UART. All right, you'll be more stable, more stable. All right. So for SPI, it is only for onboard serial communication. Remember, onboard connection. You have some other ICs together with your ATmega328, and then you can do you can write to this IC serially, send digital configurations, and then you can read back digital data reflecting the motions inside the IMU. Alright, and then we have the TWI, or we call it two-wire interface. Two-wire interface. The two-wire interface is another popular protocol for onboard communication. Only that the speed is lower. The speed is lower. The advantage of TWI over SPI is that it is only two wire, right? Only two wires. We need only two wires for communication. Alright, which is the SDA, serial data, and SCL, serial clock. We will go in depth into during the specific chapters. But just to tell you on general, so only two wires, SDA and SCL. Compared to SPI, we have four wires, MOSI, MISO, S clock, and also slave select SS. So, but because it is only two wires, all right, the protocol is a little bit different. So the arrangement of data is longer, right? Because you have lesser control wires to indicate data is sending or data is receiving. All right, so for the format is a little bit larger. The format data is a bit larger, and therefore it is a little bit slower right, compared to SPI. But still, I2C is still higher than UART or USAT. Right, so this is two-wire interface TWI. So in this single chip microprocessor, you have your basic microprocessor with the RAM and ROM, and then you have your AD converter, you have serial interfaces, serial communication interfaces, UART for you to interface with other boards outside somewhere else physically, and then you have extra two interfaces for you to communicate serially between external ICs. You might want to add external ICs, but you cannot use this SPI and TWI for long distance data transfer or communication. Okay, what else? We have also one feature of analog comparator. So built inside, you have an analog comparator. Right, so it is if you have taken the subject on electronic systems, you have your op-amp, you have your op-amp, right? You can use if you still remember, you have your op-amp. Your op-amp, this is a basic op-amp, consists of many transistors. All right, but depends on how you connect it, how you connect components, extra components to this op-amp, how you arrange the input and output. You will function according to. You can have many functions from this op-amp. So analog comparator means you're going to do some like what you call it, a reference voltage, right? Threshold or reference voltage. Usually you use a voltage divider, right? And then you have your input your input. So what the comparator will do, it will actually subtract your reference voltage to your input voltage, right? Usually comparator, for example, let's say if you take later your biomedical signal processing, if this is your ECG, ECG, why is becoming like this? Not so nice. Okay, I think it's the mouse pad. Uh, okay, let's see. Okay, this is your ECG. So uh, you can actually use some analog circuits to convert ECG signals.
Tak telinga.
into output square wave. Hello, anyone there opening your mic? Your mic, please. Your microphone. Please off your microphone. Alright. So through circuit, through some circuits, you can actually convert this ECG signal into a square wave. So one peak will become one square wave. Alright. So let's say you want to use this the built-in the analog comparator, so that when it goes over a certain voltage, it will trigger, right? It will trigger the microprocessor or certain registers inside to capture the event of a pulse. Right? Let's say you have another pulse over here, right? So the first trigger, right? You will record, you will capture the time, and then uh, after certain time, you get another pulse from the analog comparator, and then you capture the time, right? This is example lah. So from here, you can calculate the time between these two pulses, which represents your the time between the peaks of your QRS lah. From there, you can calculate your heart rate. So this is one example of how you can use your built-in analog comparator. And then you also have timer compare. Timer compare 0, timer compare 1, and timer compare 2. So for TC0, it is 8-bit, TC2 is 8-bit also, whereas TC1 is 16-bit. Timer compare is one feature where it is a function where it compares time. Of course, timer compare and timer compare and capture. So let's say you want your process to have some very precise measurement of time. Let's say you want to have you want to determine that for every 2 milliseconds, or you want to have 2.2 milliseconds, very precise. You want to do something, right? You want to do some process, or you want to read some data from outside, right? So you can use this timer compare. So when you use the timer compare, this feature will tell you after, of course, after you do some initialization. So you already started the program, so it will tell you when certain time has been reached, right? And then from there, you will be alerted. Your program will be alerted, and you can do specific tasks triggered by that time, right? So we have 8-bit time, 16-bit. Why 8-bit and why 16-bit? So 8-bit usually is you can use that for a short period of time, nanoseconds or microseconds. Let's say you want to do some long, you want to monitor a longer time, a longer span of time. Let's say you want to monitor 1 minute. All right, 1 minute for a microprocessor is very big. It's very big, because microprocessors, they work for Atmel. Their crystal is, you can use 20 megahertz, for example. So 1/20 means what? Megahertz will become micro. 1/20 will be 50. So 50 microseconds, very fast. So uh, if you want the microprocessor to monitor a longer time in minutes, so how many cycles that would be? Maybe more than million cycles. So using 16-bit will reduce the burden uh, of, uh, of the processing. So if you use 8-bit, they will be very short. So you need to have 8 times 8. Then that will be very long. So it's not suitable. So for long processors, you might want to look at 16-bit. Alright, and then we also have a feature built inside the 80 mega grid is the EEPROM. It's the EEPROM. So EEPROM is something like ROM also. It's something like ROM also. But usually EEPROM is the ROM accessible to users, right? Let's say, for example, what would be some application of EEPROM? Let's say you have your something that you do settings. You have a machine, or you have an equipment, or you have a device, small device. You do some internal setting. Okay. Let's say for example your aircon remote control. Your aircon, you have the remote, right? The remote control, right? So that remote control, right, is actually they already have program so that the remote will store your most recent setting of the temperature, of the speed of the fan, right, of the mode of operation, right? Is it cooling or is it condensating, things like that lah. So all those values, when you do setting on your remote, right, the latest configuration of your air conditioning unit is stored in the EEPROM. So it is accessible to the users in that way lah, right? So you can store data from the users in the EEPROM, right? So EE means electrically erasable programmable ROM, right? Which means that uh, you can erase the program on the ROM using electrics. Why EEPROM? I'm not sure whether I've tell you this before. Previously, when they want to when they want to program a ROM, they need to have what you call it? They need to use UV, ultraviolet. So they want to erase the data on the ROM. The chip of the ROM is also black. It's a black IC, but it has a tiny little window, right? A small window, right? And that window, when you exposes UV light to the window, all right, all those programs will be deleted, right? So at that time, during I think when I used to lab in maybe in 1998, so we still have those UV units to erase data on the on the ROM, right? So they use light. So you have to remove the ROM first, put in that UV something like a UV small cabinet. Then you expose to UV for some time, then it's erased. So imagine at that time, you need to remove your IC, you have a UV light. If your UV unit is blown, you have to replace the lamps, things like that. But now they have the technology of they've designed the method of electrically using electrical currents to erase all those memories in the ROM, right? We might usually we would take what you call it we will not usually appreciate this feature because we do not most of us now do not experience the process of erasing the ROM, right? But my seniors especially, and myself during a little bit, I think during my time it's like the borderline between the change of technology. So I get to see actually and experience, right? So but this EEPROM is built inside your micro controller now lah, the 80 mega 328. And then what else? You also have clock circuits, oscillator circuits, clock generation. Alright, so we need to have external circuit. Previously, if your microprocessor, you need to have external circuits. So you will have crystals, you will use capacitors, and also some logic ICs, so that it will generate square waves. Alright, maybe sometime later I will share with you on crystals, a very interesting device. Right, so you have some other features like watchdog oscillator or watchdog timer. So watchdog is a feature in most microprocessors now for them to monitor. So just remember the term watchdog. Watchdog, a dog which do the watching. So it's like your dog guarding something. monitoring something. So when something happens, it will react, it will take action, right? So watchdog oscillator, watchdog timer, right? So watchdog oscillator and timer usually, for example, your if your oscillator fails, the oscillator fails to function, all right, something happens, maybe overheating, maybe something happens. So the thing is, the watchdog oscillator will be aware of this, and it will stop everything from functioning, right? It will just stop everything from functioning. Also goes for the timer, right? So let's say you have a timer function. If some timer is not functioning, right, it will stop the function, right? It will stop everything. So usually it will stop and actually reset, reset. It will stop and reset, alright. But and it will observe again. If the clock does not function again, it will stop and reset again. So it will keep on doing that. So when it does that, so your program will not actually function, alright. This is actually a very useful feature lah. Right? Let's say for example, you have your drone. Now drone are very popular. You have your drone. So drone, they have microprocessors, right? And if you look in those videos in the Google, in the internet, in YouTube, they also have the guns. They have the electromagnetic guns to shoot down drones in terms of electromagnetic waves. So they can shoot the drones by sending very like a beam of electromagnetic waves. So it's something like wireless, right? There's nothing physical coming out from the gun. So it's an EMT gun, electromagnetic gun, right? You will send to the um, drone, like the flying drone. So what will happen, right? When the drone receives those bursts of electromagnetic waves, all right. Let's say for example the clock or some other or the timer might dysfunction, right? It might get lost. Yeah, the data inside might just reset and get lost, right? So watchdog, what happen is watchdog will disable the reset off the microprocessor, and after some time it will on back, right? It will on back and it will see if if the clock is still working, right? If it does not work, it will stop, right? So imagine if this is a microprocessor on a drone, so what happens is that uh, let's say there's a failure of the microprocessor, all right. Let's say because the call it the blade, the rotor is spinning, it is spinning. Let's say at the point of when it is attacked by the EMT gun, the microprocessor is already sending signals to these motors to rotate, to rotate the fan. All right. So what happens if, let's say, the microprocessor um, it becomes if it goes into the failure mode, it does not have the time to change, or it does not have the time to give instruction to the motor to off. All right. So what will happen? All right. So the microprocessor is already burned. All right. It does not work anymore. But the motors have already received instructions from the microprocessor that it should turn. So what happens that when you shoot the drone, what will happen is that the drone will not drop down, all right? It will just fly off to somewhere else, right? Just fly off to somewhere else, and you might lose your drone. So you might want a condition where, all right, when you shoot the microprocessor, uh, the watchdog will detect that, and at the same time you will still have time to disable those motors, and then the drone will come down. So this is very useful feature lah, right? Then you have your some reset function over here, right? It might seem like not important, but during our times when we do the microprocessor board doing the reset circuit, we need to have another set of circuits also. So many circuits surrounding the microprocessor. Alright, and then you have your program logic, things like that. Okay, so this is the plot diagram of the AVR for the general AVR from the 8APRIL from the 8APRIL. So basically, most of them will have these features lah, right? And you can see here, of course, you have the USAT, SPI, and TWI. So below that, I left out just now is the digital I/O ports, digital I/O ports. So you have port D, you have port B, you have port C, port C. During my time, if USAT have its own physical pins, port D have its own physical pins, port B another physical pins, port C and other cell functions. But in this case of the 80 mega or the AVR microcontroller, is that the USAT, the way they design that is that using the same physical pins can have you can share between two peripherals. For example, port D, you can make it to function as just pure digital input-output, all right? And through some programming, you can make it some pins of the port D to become function as the USAT or UART. So the same goes for port B lah. Alright, port B can function as a digital input-output, 8 pins. After some settings in the registers, we can make some pins to function as the SPI, and port C has some function as the two-wire interface. So this feature is very good lah, very good. So it means that using some physical pins, you can customize. You can do a lot of customizations. Okay, that is for the general board diagram of the AVR 80 mega. Alright. Still here, we are looking at the data flow. Just now is the what features are inside, right? And also, of course, we can see a little bit of data flow. But now here we can see the data flow better lah. And this data flow is focusing on the data bus, the 8-bit data bus. So this is how the 80 mega 328 the processor interacts between the features inside the microcontroller. Right. So if I were to ask where is your CPU, right, that would be your ALU lah, right, your ALU. So you have your ALU, you have your general purpose registers, right? So to be specific, inside your CPU, it will contain your ALU and also your general purpose registers. All right, all type of microprocessors during my time and the current processors, one CPU will need to have the ALU and also the general purpose registers. Right, and also this is internal inside the CPU. And of course, you have all the status and control lines. Status and control lines over here, your data bus over here, right? Then the addressing buses, direct addressing, and then you have the indirect addressing, and so on and so forth. And then you have your data bus is also connected to your data SRAM, right? So this data SRAM is actually is the SRAM out of the CPU, right? For this microcontroller, the data SRAM is inside the chip, inside the entire chip, right? But this data SRAM is not inside the CPU. Let's see the previous here. So you can see here, this is the CPU. Inside the CPU contains the registers, the general purpose registers, all right, and then it also contains the ALU and the ALU, arithmetic logic unit. right? So the SRAM is outside the CPU. It's not within the CPU architecture itself. It's outside. But the SRAM on the same, because this is a microcontroller, so it is within the chip itself. It's within the chip itself. So here the data SRAM is outside the CPU. Alright, whereas this data register, I mean the general purpose registers are inside the CPU, right? And this is how all those data lines are connected lah. So you have the ALU, the registers, your program counter connected on the same data bus, right? So the data SRAM is connected, the EEPROM is connected, they are sharing. So the I/O lines, the I/O module 1, 2 sampai N, the analog comparator, watchdog timer, SPI, interrupt, user and UART, things like that lah. Alright, and also your flash program memory, right, instruction register and instruction decoder. Right, so the instruction register and the instruction decoder is inside the CPU also. This is also inside the CPU. Basically, if I can highlight to you which part is inside the CPU, let me draw. So something like this. Okay, so this is inside the CPU. Okay, all right. So this is how the data is flow lah. So basically, number one. So let me see. So when you on your microprocessor board or microcontroller board, what will happen is that the first thing will happen is that you have a program counter. So the program counter is uh, is something like a manager lah. Manager, it will tell you, okay, the first thing to do is fetch the first instruction, fetch the first command from the owner, right, from the programmer first. So fetch the instruction from where? From the flash program memory, and then you will transfer that instruction into the instruction register. It will decode that. It will decode the instruction, and then it will output to the control lines. Let's say the instruction say that talk about the instruction is about commanding the CPU to take data from the SRAM and do some addition and return back like that. So everything that the instruction will be given to all to the specific device lah, according to your instruction lah. Let's say the instruction says now, okay, now read from the analog comparator. So the analog comparator will get awake and do its stuff. So that is what the instruction decoder will do lah. So after finishing its task, all right, the floor, if you have, the control will be passed back to the program counter, and the program counter will say, okay, now will take the instruction, will give the instruction, okay, now take the second instruction from the program memory and execute, right? And it will execute, and anything involved in the execution will be activated. So and the program counter will keep on doing that lah. It will start from the beginning until the end of the program. Let's say if a certain part of the program says that, okay, go back to the beginning. So program counter will tell itself, okay, this instruction says that you need to go back to the beginning. So program counter will point itself to the beginning of the program, right? So basically that's a program counter lah. Okay, so let's look a little bit on ALU, and also maybe after this on the general purpose registers lah. So the ALU is the ALU, so arithmetic logic unit. Arithmetic logic unit, the ALU. So its function is to do arithmetic and logical operations. So it do operations between registers to register. You can do operations between registers to memory and also memory to registers, right? So other than arithmetic and logic functions, right? Arithmetic means mathematical, logic means those AND gates, OR gates, NAND gates, things like that. And you also have the ALU will also do the bit operations, like bit set, bit clear, right? So yeah, let's say you have your registers. Registers is 8 bit. So you can define from bit 0 to bit 7 which one you want to do operation on, right? But you can we have instructions for that to do operations of bits. We call it a bitwise operations. You want to take the bit out, you want to set it, you want to clear it, you want to do some operations like logical, like AND or between the bits, and then you store back the values, things like that lah. Right, so that's for the ALU. And then we have our registers. So registers, like I said just now, it is not contained in the data SRAM. It is out of the SRAM. Alright, so it's a different mechanism. It's not on the same. It's not on the same architecture. Right. That's why you can see if you want to transfer between registers to RAM, you need a bus. You need to use the bus. The data SRAM, of course, you can transfer data between general purpose registers to data SRAM, but you have to use the bus. Pass the data to the 8-bit data bus, and then you can go to and from the RAM, right? But the 8-bit general purpose registers, they might function like a RAM, because they if you have values in there, when you off the microcontroller, right, those values will disappear. Okay, but the purpose is not for users lah. It is for internal call it internal operations, internal operations. Whereas for data SRAM is usually when you want to store data from the users. So you can store them in the data SRAM. Right, I might ask you questions like what's the difference of functions between data SRAM and general purpose registers when both are store temporarily, both can store temporarily. So you might want to elaborate on that, right? So inside this general purpose registers, total we have a total of 32 8-bit general purpose registers. So they are distributed to basically three categories. You have your status register, then you have your general purpose register file, which also includes your X register, Y register, and Z register. Then we also have your stack pointer. So stack pointer high and stack pointer low. You will try to understand this after this. Okay, for status register, all right, it is an 8-bit register, all right. So the name is SREG, SREG, status register. The address is located at is it 03F? 03F. Where is it that did I put my registers? No, it's not here. Right. So basically the address is at 03F, right? Or I think this is all, depends on microcontroller versions, or 0x5F. Later I will check back, or you can check yourself for 80 mega 328 what is the address of the status register, right? So basically we have 8 bits. So each bit represents a function, right? So if it is high, it means something. If it is low, it means something, right? The same goes for the other bits lah. So you have the T, you have the H, you have the S, V, N, Z, C. So every bit has a function, high means something, low means something. So for the first one, we want to look is the bit 7 or the I status register, the I inside the status register. So it represents the global interrupt enable. So what it means here is that if you put a high, if you set this bit, set or put a high, so it will enable all interrupts, all interrupt functions in that microcontroller, right? If it is set to 0 or if it is set to clear, all right. If it is clear or set to 0, so even though specific interrupts, like your ADC interrupts, you can have timer interrupts. If your interrupts is enabled, but when the global interrupt is disabled, or when you put a low over here, so every or all internet interrupts will be disabled, right? And then okay, let's say when interrupt occurs, this one if you when you enable it you enable it, right? This is global interrupt, right? To enable all the interrupts, because because you can have many interrupts. You can have interrupts from, let's say, analog comparator. You can have interrupts from ADC or IO module, right? So this is specific interrupts. But we have a register. We have a bit in certain register which controls everything. Everything. So the thing is, like I said, previously, if you have an interrupt, you have your main program running, right, and then an interrupt happens, and your program will focus to that small function of the interrupt, right? So during that time, you cannot have other interrupts, because of course we have many interrupts features. You can enable many what you call it? You can enable several interrupts. Like ADC interrupts, you can enable one time together with the interrupts for HPI, for example, right? Uh, but even though an interrupt happened, right, we cannot afford to have another interrupt function disturbing the interrupt process or the interrupt service routine, the ISR. So when one interrupt happens, right, what will happen is that automatically the by hardware, this bit will be set to low, right? When it's set low, any other interrupts cannot happen, right? Because why we don't want the other interrupts to happen? Because we are now currently servicing an interrupt service routine, interrupt service routine, right? We have exited the main program. We are going to service an interrupt routine. So uh, the what you call it? Other interrupts will be disabled. So how do you do that? Is by you setting low or clear, right? Set low over here to the I bit, so that no other interrupts can disturb this interrupt process, right? And then usually your interrupt process you will end with a simple a single line of instruction. We call it the RETI, return from interrupt. So you need to put a code there, a line of code there, return interrupt at the end of the interrupt service routine. So when you finish your process inside the interrupt, when your interrupt triggers, you finish the process. At the end, you write the RETI. So when the microcontroller sees the RETI, you will automatically set back the I to high, which is to enable other interrupts, because we already have finished this interrupt. So after finishing the interrupt, you want to go back to the main program, right? At the same time, you want to enable other interrupts, so that other interrupts can happen when it is required, right? So this is how it works. So at the end of ISR or interrupt service routine, the RETI will set the I bit to enable subsequent or other interrupts to happen. So alright, this is about the interrupt bit, global interrupt enable. So you can also other than RETI, this is done automatically lah. Okay, when something happens, when the interrupt happens, right? You can also based on customizations, right? You want to have more control on the process inside the program of the microcontroller. You can also set the you can set or clear the interrupt bit here over here by using the instruction SEI set interrupt or CLI clear interrupt. Okay, this is on interrupt. So are we? Yes, we are over one. Okay, I think that's all for this session. So in the next session, we will continue with the next bit in the status register, which is the bit copy storage, and then followed by the half carry flag, followed by the sign bit, and the overflow and negative flag, and finally with the 0 and carry flag. Alright, so thank you everyone for this your attention and attending this session. Alright, thank you and bye bye.
Thank you, Doctor.
Right.
Thank you, Doctor.
Thank you, Doctor.
Alright, welcome.
Thank you, Doctor.